We've all seen the photos and video footage. A multi-ton apex predator launching its entire body out of the ocean like a missile, defying the laws of gravity to crush its prey in a spectacular explosion of power. This behaviour is the definitive image of the great white shark, one of the ocean's ultimate hunting machines. But behind the scenes of these dramatic images, marine biologists and shark scientists have documented a somewhat different reality. If you watch these hunts day in, day out, away from the heavily edited Shark Week TV shows and documentaries, you discover a pretty crazy statistic. Nearly 60% of all white shark predatory strikes end in total failure. Think about that. One of the most revered ocean predators on Earth loses, or at least doesn't win, more than half of its battles. Every single day, these sharks burn huge amounts of metabolic energy on vertical breaches, only to come up with nothing but a mouthful of seawater. So to figure out why, we've got to look at one very specific ecological arena, Seal Island in False Bay, South Africa. This was once one of the very few places on the planet where these extreme vertical ambush breaches happened frequently. Here, two ocean animals are locked in a tactical war centering around a specific section of a scrap of rugged rock: the great white shark, Carcharodon carcharias, and the Cape fur seal, Arctocephalus pusillus pusillus. Today then, we're jumping deep into the peer-reviewed science, and together we'll uncover the hidden mechanics of this underwater battlefield. From underwater optics, water depth and topographies to a seal's sheer acrobatic agility, we'll figure out how this prey species outwits one of the world's most famous predators. Most of the time, anyway. Welcome back to another Shark Bytes episode, everyone. Now, for us to understand why a white shark hunt succeeds or fails, we've first got to understand the map. Seal Island isn't just a random rock in the ocean. This aptly named island at certain times of the year is crammed with up to 70,000 Cape fur seals. During the winter months here from May to August, young of the year seal pups under a year old have to leave the safety of the rock to forage out in the open ocean. To get to their feeding grounds, the seal pups have to cross a deadly perimeter known as the Ring of Peril, which is anchored by a specific site often referred to by scientists as the launch pad. No guesses as to why it got that nickname. Whee! But the sharks here aren't just randomly swimming around this section of the island, hoping to bump into an unsuspecting seal pup. These predators are calculating tacticians. Back in the late 2000s, in what I think is an amazing crossover of scientific disciplines, shark researchers Aidan Martin and Neil Hammerschlag teamed up with criminologist Kim Rossmo. Now, I'm guessing lots of you are wondering what a criminologist is bringing to this shark research table, right? Well, with Rossmo on board, the team were able to apply a technique called geographic profiling to the data that they had on white shark hunting behaviour. Geographic profiling is a mathematical tool that was originally developed by criminal investigators to track serial killers. Specifically, it was Kim Rossmo who designed it in the 90s. By mapping the spatial locations of a series of connected crimes, the algorithm here can calculate the most probable location of the criminal's home base or anchor point. For any of you serial killer aficionados out there, the technique was pretty fundamental in catching one of America's most prolific serial killers, Gary Ridgway, aka the Green River Killer. Back at Seal Island, though, the researchers inputted the GPS coordinates of 340 natural predatory interactions observed between white sharks and Cape fur seals. And by plugging this data into the geographic profiling software designed by Rossmo, they were hoping to figure out if the sharks here were operating from a distinct, predictable anchor point. And their analysis ended up proving that white shark search patterns are absolutely non-random. The sharks here maintain distinct anchor points, focusing their hunting efforts in incredibly specific zones, primarily off the south and southwest sections of the island. Why? Well, because that's exactly where the vast majority of seals leave and enter the island from. The launch pad. But if we look closer at the topography of these anchor points, we can see that the sharks are clustering in areas where the water depth drops off rapidly to between 10 and 20 meters within a very short distance from the shore. Which brings us to our first major hunting constraint on these white sharks: water depth. A white shark can't execute its signature vertical breach in shallow water. For an ambush to truly work here, the shark has to cruise close to the bottom, keeping its dark dorsal coloration blended with the rocky sea floor to remain invisible from above. By using this geographic profiling technique, the scientists could prove that the sharks were choosing their anchor points based on a perfect sweet spot, deep enough to remain hidden and build upward momentum on their strike paths, but close enough to catch the seals right as they bottleneck near the island's entry and exit points. Although, despite this pretty mathematical precision on choosing where to wait, the sharks here still fail nearly 60% of the time. And to understand why, we've got to look at what happens when the clock starts ticking at first light. Hunting at Seal Island is largely governed by a relatively strict clock, and when you look at the data, shark predatory activity isn't evenly distributed throughout the day. It peaks dramatically during two tiny intense windows, also known as crepuscular periods, effectively within an hour or so of dawn and dusk. During those low light periods, data from follow-up research showed that white shark hunting success often exceeded 55%, but as those crepuscular periods began to wane into more bright light conditions, the shark success rates dropped to below 40%. And all this comes down to how light behaves when it passes from air into water. At dawn or dusk, the sun is positioned at a very low angle relative to the horizon, and when light hits the surface at an acute angle, a large percentage of that light is reflected away rather than penetrating into the ocean. And so for a shark cruising along the seafloor at 25 or 30 meters, looking up towards the surface, the sky acts like a faint backlit canvas, and any seal swimming at the surface ends up being perfectly silhouetted against the backdrop of the sky. But for the seal looking down, the depths are pitch black, and the water column scatters and absorbs what little light enters, meaning the seal has minimal to no downwelling visibility. Although when that sun is higher in the sky in the hours after sunrise or before sunset, more light rays pierce down into the sea, and suddenly the water column lights up and the light reflects off the shark's grey dorsal skin, blowing its cover. The seal's visual detection distances actually increase exponentially with increased light penetration, and once a seal can see a few meters into the depth, the sharks lose their element of surprise. And without that element of surprise, the white sharks are at a tactical disadvantage. It's clear then that the seals here have pretty sharp eyesight, and so to overcome this, the white sharks have to rely on one of their most devastating attributes, their speed. But how much space does a 2-ton fish actually need to hit its top speed? Well, thanks to some very clever kinematics calculations in the research paper, we know the exact physical constraints of a white shark charge, so let's briefly break down the maths. The absolute minimum distance a white shark needs to accelerate from its cruising speed to its maximum attack speed when initially striking is 3.76 meters. That's about 12 feet of vertical runway just to get revved up to full power. But that's only the acceleration distance for the shark itself, so to understand the total distance required for a successful ambush, we also need to factor in the seal's detection capabilities in those low light conditions. Based on some underwater optical measurements at dawn, the average distance at which a seal can spot a dark silhouette moving up from the gloom is thought to be around 2.6 meters. And so when you combine these two values, you get a distance threshold of 6.36 meters. And this is the absolute minimum depth required for a white shark to execute a fully powered ambush without being detected before it reaches top speed. If they try to strike from a depth shallower than 6.36 meters, the seal has more time to react. And it's these very specific depth measurements that helps explain why the geographic profiling model we looked at earlier shows the sharks basically completely avoiding the shallow waters hugging the rocks of Seal Island. The white sharks are bound by the simple laws of physics. They need that deep water column just like an aeroplane needs a runway. By the time the shark clears its runway and enters that seal's 2.6 meter visual detection zone, it's traveling at a whopping 11 to 12 meters per second, nearly 27 miles per hour. And at this speed, it closes that final 2.6 meter gap at 0.25 seconds, a quarter of a second. It's about the same speed as a single blink of the human eye. If the shark hits its target in that quarter-second window, the hunt's over in spectacular fashion. But if it miscalculates by even a fraction of an inch, or the seal detects that incoming massive pressure wave, then the battle enters a whole new phase. And in this phase, the shark's multi-ton advantage becomes one of its biggest hindrances, because if a white shark is so fast and hits with such blinding speed, how does it manage to lose in nearly 60% of its hunts? Well, the answer here lies in the counter-strategy of the Cape Fur seals, vigilance and agility. When an initial strike misses its target, the hunting scenario shifts instantly from a high-speed explosive ambush into what biologists call a secondary tail chase. And this tail chase is similar to what you're seeing on screen right now from a camera-tagged white shark. In real time, it's enough to make you dizzy, but this is what it looks like when a white shark is trying to chase down a seal. If we slow it down, you can see that seal twisting and turning underwater, darting in random and unpredictable directions, and within a split second it turns back towards the shark and it's gone. a failed hunt. If we compare the physical metrics of both of these animals side by side in terms of their average mass, locomotion type, and turning radius, we can see that there's a pretty big difference between the two. The massive white shark uses its size and power through its stiff tail and rigid streamlined body to generate huge straight line speed, whereas the Cape fur seal relies on a different kind of propulsion. Here the seal uses its highly flexible and powerful pectoral foreflippers as well as its dynamic skeleton, allowing it to bend and pivot its entire body weight on a dime. It's nimble and acrobatic. As soon as that initial ambush misses, the shark loses its momentum, and even though it's still quick and powerful, it becomes a 1-ton behemoth trying to turn and catch a 50-kilogram mammal. The behavioural data we have to support this, I'd say, is clear as day. From these graphs here, you can see that if a hunt lasts for longer than a minute, or it involves more than 2 subsequent surface lunges, the shark's success rate, those black bars you can see, drop to almost 0. If the shark doesn't win in the first few seconds, more often than not, the seal wins by default. And so knowing that the tail chase is a losing battle, the white sharks here have to maximise their chances of success even before they begin their ascent, and they do this through highly specific target selection. They're not just attacking seals at random, they're looking for certain behavioural weaknesses that they can exploit. And this target selection can be seen in the highly specific demographic that the vast majority of sharks here choose to attack: the lone young of the year seals. These lone pups are so uniquely vulnerable because of 2 biological factors: shared vigilance, or lack of it, and something called postprandial torpor. When Cape fur seals travel in groups, they all benefit from something called the many eyes effect. All eyes are essentially looking down into the water column, and if one spots something in the depths, the group reacts. But a lone pup swimming back to Seal Island by itself has no shared vigilance. It's got to look out for itself. What's even worse though is that these pups are often returning from multi-day feeding trips out in the open ocean where they've gorged themselves on fish and squid. And after a big meal, the seals are experiencing a physiological state that I just mentioned to you: postprandial torpor, or in normal speak, and something that we can all relate to, a food coma. Their bodies divert oxygenated blood away from their muscles and brain to focus on digesting the food in their stomachs, leaving them more sluggish and significantly less alert. But even against some of these exhausted lone juveniles, if that initial ambush lacks precise alignment, the pup's basic survival instincts can still trigger an acrobatic escape, leaving the shark empty-handed. When you look at all of these puzzle pieces together then, the strict requirement for deep water runways, the incredibly narrow light windows, the agility of the seals, and the lumbersome size of the sharks, it becomes a bit clearer as to why nearly 60% of these hunts fail. But being these masterful predators evolved over millions and millions of years, the sharks don't need a 100% success rate to thrive. Just one successful predation on a young Cape fur seal delivers a huge payout of high-density energy. That blubber provides the shark with tens of thousands of calories. And so while the energy burn during a failed vertical breach is significant, it's relatively small compared to the calorific reward of a successful strike. Mathematically, these sharks can afford to fail 5, 6, even 7 times because just one successful strike more than compensates for the energy spent during those missed attempts. In my opinion, this 60% failure rate isn't a flaw in the white shark, it just shows how balanced this ancient ecosystem is. Because if white sharks succeeded 90% of the time, say, they'd wipe out that seal colony pretty quickly, destroying their own food supply. The high failure rate keeps this entire marine ecosystem in a state of equilibrium. Well, at least it did, because in 2016, something strange happened in this part of South Africa because the white sharks here virtually disappeared. For a long time we believed killer whales were entirely to blame, but in this video here, I show you how it might be a few other hidden factors that contributed to their disappearance. So if you want to know why the white sharks of Seal Island, False Bay and the surrounding waters basically vanished, make sure you give this video a click. Go on, I'll see you there.